Yeah, I'm looking pretty good these days. Yeah. Oh my God. PowerPoint on the bottom, Chris, please.
Your face is frozen in a smile right now.
All right, all set to go. All right, good morning, everybody. How are you? Jim DePalma here for Advanced Hydronic Training, week number 2. Backing me up today is Mr. Rob Clemens, so please type in any and all questions to Rob, and he will do his best to answer them and or bring them to our attention as a group, and we'll talk about them. In the background is the marketing team. Brett is here. He runs our marketing department, and Christiana is running the board, so she will keep us all in line. All right, so we're jacked up on Krispy Kreme donuts. You can see I can't even talk. We're so full of sugar. So we're all excited today. So here we go. We have a lot to cover, so we're going to head right into it. Session 1, any questions from last week when John did his presentation? That was really to set you up for today, because each week will build on the week prior. So if you have any questions, please type them in. Let Rob know. Anything you want us to review quickly before we get started? So as we're waiting for some of those to come in, let's do some housekeeping. On your screen, you do see the hash marks that are either on the top of your screen, maybe I'm on the top, maybe I'm on the side. If you click on those hash marks, you can expand the presentation or make it smaller, make me smaller, whatever you'd like to do. On the left-hand side of your screen, you should see the arrow where you can click on that, open up that box, and that's your chat box there when you can type in questions.
Right-hand side.
Okay, right-hand side. And you can type in your questions, plus the downloads that are there. You're really going to need them today because we are going to be working in the Takeo catalog. We're going to be using the tech pages in the back. There's also a floor plan because we're doing a heat loss today. We're going to design a system from top to bottom today. So we need that so you can play along. So Robbie, any questions from last week?
Just one. Gentleman wants to know if they can get NATE credits as far as this class is concerned.
Unfortunately, no. This class does not generate NATE credits. We could send you a certificate if you choose, if that would help you with your employer. This shows that you're on the class, but no, we don't provide NATE credits. Anything else there, Rob?
No, sir.
All right, let's get going. We got a lot to do. Again, I'm jacked up on Krispy Kreme, so hold on. So our agenda for today, we are going to go over system design. We designed this week based on the premise that you may be a fabulous installer and the boss gives you a box of stuff. You show up on the job and there's another big crate with the boiler in there, and he says, put this all together. And you do a fabulous job doing that, but we're under the impression you may not understand why you're doing what you're doing. How did he come up with the size of this boiler, the size of the circulators, the piping? How did all this occur? So this is what we're going to go over today. Then we'll go over the typical heat load distribution, how we're going to get the heat out into the system. What options do you have? Then we will cover circulator sizing, pump curves, and system curves, because every system that you design will have its own unique fingerprint, which what we call is the system curve. And that's really important to understand. And then we'll kind of follow up with our webinar that Anthony Tassi did about 2 weeks ago, I believe, on low temperature systems, where he was talking about cast iron boilers, condensing boilers. And we're going to go a little bit more into detail on maybe the differences and how we're going to approach them in our system design. All right. So first things first, in your downloads, you would have had the Takeo training takeaways, which is going to explain how to do a heat loss. It's critical nowadays to do heat losses and also heat gains if you're doing cooling systems. Generally in our territory where we operate as Wales Darby, in order to get some permits now, you have to produce a manual J. You have to show that the inspectors that you've done the work, you know the BTUs, and you've done the right amount of research in order to size the equipment properly. To let you know what's inside the manual J is what this Takeo takeaways is all about. This is the math, all right? Now, there's all kinds of different software programs out there to do these heat losses. Manual J is just one of them. Uponor LoopCAD does a heat loss. It does it based for a radiant system, or you can do it for baseboard. It does not matter. SlantFin always had a program out there. There's a whole bunch of different ones. Some of them are free, some of them are a subscription, but you really should be comfortable in understanding how to do this, because for the guys who do this, this is going to give you a huge advantage versus your competitors who don't. You'll be able to size the equipment exactly down to where you need it to be, and that will give you a distinct advantage when it comes time to purchase your material. Somebody else may be just exchanging material for material, BTUs for BTUs, and there's a very good chance in the world of boilers that boiler was dramatically oversized. So this will give you a very good price advantage. So what are we looking at here? It says heat loss. IDT minus ODT equals DDT. What do you think, Rob? How's your DDT today? So IDT is the indoor design temperature that you want. So for today's exercise, we're going to use 70 degrees. ODT, outdoor design temperature, that would be what is considered your average coldest day of the year in your territory. So right here in beautiful downtown Warren, New Jersey, our average coldest day is 14 degrees. Now, we can get colder than 14 degrees, but that will happen less than 2% of the heating season. And this heating season was a great example of where we play. We had days of 14 degrees. We've had days where we woke up and it was single digits. It was 5, 6, 7, 8 degrees up near me. And then we had a lot of days where it was in the 40s and 50s. So our heating season was all over the map today. But still, on the average, 14 degrees would be our coldest. We plug 14 under ODT. And then you got DDT. That's your design temperature difference. So if I take 70 and I subtract 14 from it, my DDT will be 56. And that is what we're going to use today when we do our heat loss. Okay? Now, next is infiltration. We have to figure out what the infiltration factor will be per room. So we do this per room. This is not a block load type of deal for the building. This is on a room by room basis. So, excuse me. So what you have to know is whatever room you're working with, how many outside walls does it have? And if we have outside walls, we'll have windows and or doors. So do you have one outside wall? There's the factor 2, there's the factor, and 3, there's the factor. And we would take our room dimensions, the length, the width, the height, times the design temperature difference, which is 56 in our instance, and we'll use that infiltration factor, and we'll get a BTU. Then we're going to do it for the doors and or windows, and in doing that, we do have to figure out a U value. And to get a U value, you're going to take 1, and we'll divide it by the R value. Where do I get the R value? Well, that's basically the insulation factor of that type of product, right? So think about your walls that could have an R11, an R15, an R19, an R25, Same thing with ceilings. You could be at R20, 25, 30, or higher if they're spray foaming. So to figure out what the U is, we're going to divide 1 by R. Then we'll figure out our net wall area, and we'll take away our windows. And we have to use that U factor, get that BTU. Then we're going to do the same thing if we have exposed ceiling and if we have exposed floor. Okay? So, Chris, if we can go to the board, please, behind, if you could zoom in there. So here's our room. I put together a room for you guys, and this happens to be my master bedroom at my house, which has 2 exposed walls, no heat above, and is over a crawl space. So it's a big, big challenge of a room to heat, all right, to make comfortable. So on the left here, I hope you can all see that we made up our U factors. So to get the U factor, we divide 1 by R. I'm going to go over here instead. And then so for my glass, which is an R value of 2, 1 divided by 2 is a 0.5. So for my glass, I'm going to use a 0.5 for my U factor. For my walls, I probably got an R15. The house was built in the 50s. So to do that, we end up getting a 0.067 for my U factor for my walls. Ceiling's about an R25. I should tighten that up. And that U factor then becomes a 0.04. And then I am over a crawl space, so I did have to insulate my floor, so that U factor becomes a 0.09. All right? I believe that is a 0.09. Yep, it's 0.09. So these are the U factors that we're going to use in this heat loss for this particular room. So the room is 14 by 12 with 8-foot ceilings. So I got my 14, my length, my width, my height, times 56, my design temperature difference. So if you plug those numbers in, gentlemen, and math it out, you'll get 1,354.75 BTUs. Then the square footage of glass in this room is 28 feet. All right, so 28 feet times 56, again, my design temperature difference times the U factor of 0.5, then gives me a BTU of 784. Then my walls, right? I've got a 14 and a 12-foot wall. That's the running linear feet of my outside walls. Add that together times 8, I get 208, but I have to subtract the square footage of the glass. That's where the 28 comes from. So I get 180 times 56, which is my design temperature difference, times my U factor of 0.067 to get another BTU of 675.36. I have to do my ceiling because my ceiling is exposed. So the 14 times 12 times, again, the design temperature difference of 56 times the U factor of 0.04 gives me 376.32 BTUs. Same thing for the floor, except the U factor is 0.09. Add all these BTUs together for 4,037.15 BTUs. That's what that room needs in order to maintain a room temperature of 70 degrees. That was a speed date on how to do a heat loss, but that's what you're seeing in front of you with this takeout design, the takeout takeaways. And I just plug numbers in on a particular room in my home. Questions? Robbie, what do you think? You were looking at it saying, what's he doing here?
I don't understand how you got the 1354 for the room.
Well, it's 14 times 12 times 8 times 56. That should be the math if I mathed it right.
No,
Did I do it wrong?
I got 75,264.
How'd you get that high a number?
14 times 12 times 8 times 56, yeah.
Really? Hang on. I could have fat fingered something. That's easily done. So 14 times 12 times 8 times 56. Holy mackerel, you're right.
I think we forgot something there. Something's not right with that equation.
Yeah, something's not right. What did I do wrong? Oh, this is embarrassing.
Sorry.
Thanks, Rob. Well, anyway, that's what you would do here. Length times width times height times some. Oh, I forgot the infiltration factor.
Yeah,
No wonder why. Yeah, I'm sorry. Yeah, I forgot the infiltration factor of, and it's 2. I'm sorry.
Now it makes sense.
Now it makes sense. I forgot the infiltration factor of 2 outside walls, right? Which is the 0.018. Sorry about that, guys. We got to plug in a 0.018 right here, and that's how you get that number. Oh my. Well, as they say, stuff happens. Okay? I hope that made sense. That's a little embarrassing, but it happens. Okay?
Sorry, Jim.
No, that's fine. And I even have it written right in front of me. Shame on me. Okay. So moving forward then, we would do this on a room-by-room basis. So my next slide, Chris, if I can have control, please.
Real quick, Jim.
Yes.
The chart that you were just looking at, it's in the Takeo catalog on what page? Do you know off the top of your head?
That chart was part of our downloads. So it's not in the Takeo catalog.
Which one is that?
The Takeo takeaways.
Takeo takeaways. Is that actually in here? Because I don't know.
I'm sorry?
You didn't give me that one, just upload.
Oh, great. We're really striking out today. All right. So we didn't send the takeaways. My bad again.
Is there any way
We should just stop and eat donuts, huh?
Is there any way we can get that on there real quick? Because
Not when
Or you
they,
can send it to them after.
Yeah, we'll send it to you guys after.
We'll send it to everybody afterwards.
All right, live podcast. Here's what happens for wide webinars. Here's what happens. Jeez. All right.
And then I got another question, actually. So this gentleman is asking, so you're saying 7 feet of baseboard is what you have?
In that particular room, that's about right. Yes. Actually, they ended up putting 10 feet in. All right. But yeah, that's all I have.
Okay.
That is correct. That is correct. It's a tough room. It's a very challenging room. All right. I have other problems there. I need to really tighten up the whole house. I can tell you this, by sliding the house and putting Tyvek wrap around the house made a massive difference, and also replacing the windows with better windows. Because at one point, 2 of the windows were just single pane. And oh my God, I could feel cold air just washing over my face laying in bed. It was rough. But now with all those changes, the room's quite comfortable. And that particular room, by the way, is zoned to the front of the house. That particular loop, right, encompasses the front of the house, and it goes and covers that area of my home, which is in the back. So that thermostat is in the front of the house. So the way to get around that is I have an Ecobee stat in the front with a remote sensor in my bedroom. So now I get an average temperature reading between the 2 rooms. Comfort level in that room has changed completely. Now that 7 feet or 10 feet, the gentleman's thinking really well. He probably did it based on high temperature, which is, one way of doing it. But we're going to talk about options today about doing this with also low temperature systems. Again, dovetailing off of our low temperature webinar that we did about 2 weeks ago. All right.
All right. And then one more quick question. So all the values we have to multiply by the infiltration factor, not just the room that you're pointing out.
Well, every room will have a different infiltration factor, because you could have a room with just one,
Yep.
well, with just one exposure. I can have a room with 3 wall exposures, right? 2 wall exposures, right? They'll all be different. All right. My wife's office, 1 exposure.
But there's always going to be an infiltration factor.
Has to be.
Yep.
Yeah. And basically, what are we figuring out, guys? We're figuring out the BTUs we're losing that we have to replace. All right. That's what we're figuring out here. Okay. So again, on a room by room basis, very, very important. If you don't know the BTUs per room, then designing your system is going to be very, very difficult. All right. Going forward, so this was part of our download for today. This would be our floor plan that we're playing with today. And normally when we do this live in person, we would have you guys do a couple of rooms doing the heat loss that I just did on the board. Obviously, don't forget to put the infiltration factor in. All right, but what we did today is we did the heat loss for every single room, and a grand total there, as you can see, of 52,320 BTUs for this project. So we have to satisfy this. We have to pick a boiler, and then we have to decide how we're going to deliver the BTUs in this project. So today I'm making some decisions for us. All right, so we're going to pick a condensing boiler because they're gaining more and more momentum, and we see more of them replacing cast iron, and that's why it's really critical that you do that heat loss. Okay, so when we do pick a boiler, and this happens to be the NTI boiler. This happens to be the NTI TRX boiler. The spec page on the boiler gives you a tremendous amount of information. And if we go back to our plan, you can see there's a master bath and a single bath. So I probably have 2 showers in this project. So I can decide to do this either as a standalone water heater for the baths, for the domestic hot water, or as an indirect, or as a combi. And we seem to get a lot of people running to the combi. So we'll use a combi today in our design, but what we want to be aware of is that we size the equipment as close to the load as possible. And if our loads between our domestic and our space heating get dramatically different, and there'll be projects in our territory where the domestic load is much bigger than the space heating load, then we have to address that separately, okay? All right, so we don't ever want to oversize a combi boiler for the domestic when the space heating load could be a lot smaller. But today we're going to use a combi. It's 2 bathrooms, 2 shower heads, not a big deal. So again, there's the NTI TRX. All right, when you look at that boiler, Chris, if you can pan over here, I'm thinking the camera will pick this up. Well, maybe not. I'll move it a little closer. Whoops. All right. This is an appliance design. All right, so the jacket actually is, yes. Whoops. The jacket has the color of Mercedes-Benz. It's a Mercedes-Benz color. That all right, Robbie? All right. Then we get the lights on there. Okay. Very simple control here on the bottom. So this is actually designed to be within living space, because in Europe, that's what they do. They don't have basements. It's not designed to be laying in a basement. So in our world, it would be in a basement or maybe up in a closet, up on the first floor. Okay. We're going to have a 2-pipe system. We're going to bring in combustion air, and we're going to have our exhaust. Depending on how you set up your system, depending on the temperature of your system, will determine the material you're going to use for your venting, and we will go over that. All right, Chris, I'm going back to the PowerPoint. So on your screen, that is the spec sheet of the boiler. So the first 2 columns you see on the left under TRX 85 and 120, those are heating-only boilers. And then next to it, the C boilers, the TRX 110C or the 150C, those are the combis. So we're going to give you the heating input. You can see the range of these boilers. These are modulating condensing boilers. They will condense if you're running them in the condensing mode. So if you were on our low temperature webinar that Anthony did, he went into great detail on what return water temperature you need. You need to have a 130 return to start to enter the condensing mode. And the colder it comes back, the higher or the more efficient the boiler becomes. So you see the range, the 9.4 to 85,000 BTUs. These are modulating boilers. These boilers can fire as low as 9,500 BTUs. So this is 11 to 1, a 10 to 1 modulating boiler. This is a big deal. You want these boilers to follow outdoor temperature, all right? Because the heat loss, we just did a speed date heat loss behind me, and we based it on the average coldest day of the year. It is not the average coldest day of the year every year during the heating season. It varies all the time. So our heat loss will vary hour by hour. So if the boiler can adjust its output based on outdoor temperature, this particular boiler has the ability to connect to the internet in it. I need another donut. All right, gosh, needs to be. You can connect it to the internet, so you can follow internet weather if you choose. So we can be exact where we have to be. So if our boiler can match the amount of BTUs that the building should be losing at that time, that's how I can have the most efficient system possible. So you'll see also the input of the domestic hot water, and you can see the range that the boilers can produce. Then you'll see the AFU, right? That is where they test these boilers, and you'll see 96, 95%. Gentlemen, if you remember from Anthony's webinar, you're talking 120 to 140 degree water temperature. All right, so we need to get these boilers in the condensing mode. We need that 130 and lower coming back to make these boilers this efficient. Heating capacity, that would be what we call, let me see, and we also have the net. All right, so heating capacity, that would be considered our DOE rating. The DOE is Department of Energy. That rating is higher than the net rating. And what does that mean? That DOE rating or heating capacity rating means that the boiler is installed within conditioned space, meaning that the room that the boiler is in is heated. So any losses coming from the jacket, which will be minimal on this boiler, by the way, but any losses coming from the jacket and or the near boiler piping, right, would be contained within the building. We're not losing that. The net rating means the boiler is now installed in unconditioned space. Is this in a garage? Is this in a basement that's unconditioned? We had projects along the shore where the boilers were underneath the house, open to the atmosphere. So that rating there is assuming I'm going to lose 15% off of the jacket and off of the piping. So that by knowing where the boiler is going to be will determine also how you pick it based on the BTUs that you need. Then we're also showing you the flow rate here for domestic hot water. On a 77-degree temperature rise, our average incoming water here is about 50 degrees. We have a really cold winter. It could dip down to 40 degrees for a while. So those numbers really fit our territory here. So you could see on the 110 combi or the 150 combi that will give you 2.7 GPM flow rate or 3.5. All right. I have 2 bathrooms on this job. I don't need a 3.5 flow rate here. 2.7 is going to be adequate. Now, unless you have a car wash shower in this particular house, you'll have to make adjustments. You may not be able to use a combi. You may have to use an indirect because you need a big dump, all right? Or you may need standalone domestic hot water. But in this project, dump of water, Rob, sorry. But in this project, he's bad. But in this project, since we have the 2 bathrooms, we're going to stay nice and tight to the 110C, okay? And then we give you your venting sizes based on length of run and all that kind of stuff. So we're going to pick the TRX 110C for this project, all right? Any questions on interpreting these specs pages? Because every boiler comes with one.
So I got 2 questions regarding the boiler itself.
Yes.
One, it has to be 2 zones if piped in 3/4. Excuse me.
Oh, we're going to go over zoning. You guys are going to tell me, and then I'll show you what I picked. So yeah, not necessarily.
And then we got another one here. If you don't get to condensing temperature, what efficiency are you running at?
So we see a lot of these boilers installed, and they don't put the outdoor sensor in. And when talking to the contractor, a lot of them take off the outdoor sensor because the homeowner complains that it doesn't feel the same as the cast iron boiler that they had. Cast iron boiler is going to be putting out 180, 190, maybe 200 degrees. So they're used to a blast of heat because that system will heat up the house pretty quick. All right. The difference here is we're going to be just modulating along, going up and down as needed throughout the day. So really it's a very gentle, even heat. The customer doesn't feel it as the same. So one thing that the boiler has built into it is an auto boost, where if the customer feels it's taking too long to get the temperature, you enable the auto boost. It will raise the temperature until we hit set point 10 degrees, and the next call for heat, it will shoot for that water temperature set point and change its output throughout the day in order to meet demand. So that's one way to get around that feeling difference. But to truly answer your question, if I'm not in that condensing mode, but I'm not at 180 degree supply water temperature, you're going to be in the high 80s. So I'm not going to hit that 95, 96, but I could be in the 88, 85, which is still better than a standard cast iron boiler at 82%. But, you know, if we did our homework and design our system properly, we can make these guys sing all day long in the condensing mode. There will be times where in the design, especially in a retrofit system, that may be in the coldest times of the winter, I will not be in condensing mode. But if I can be in condensing mode for 80 or 85% of the heating season, you're doing quite well. That boiler's doing the best it can to save money for the homeowner, right, to run as most efficient and deliver that comfort that they need. Anything else there, Robert?
Shouldn't we decide on heat emitters prior to selecting the boiler size?
Well, let's get to that too. That's part of today's program too. So let's get cracking here. Since you brought that up, my next slide happens to do with heat emitters. So baseboard, every single baseboard manufacturer gives you a spec sheet that tells you the output of their product. So a lot of guys we meet just think baseboard is a 180 degree type of system. You know, who says it's 590 at a 1 GPM? Who says it's a 580? Some specs will say it's in the 600s. Well, you have a 4 GPM or a 1 GPM. If you're not exactly sure the GPM you're going to be able to deliver, you go to the 1 GPM side of this chart. So compact is a very popular baseboard in our territory, and guess what? We sell it. So that's our baseboard of choice today. And as you can see on 1 GPM at 180 degrees, this is a 590 590 BTUs per foot output. But I have other temperatures there. So the importance of doing the heat loss, all right, that speed date heat loss that I did earlier, the importance of doing that is you may find that not only was the boiler oversized in Mr. and Mrs. Smith's house, excuse me, but also the baseboard. So since that was my master bedroom in my house, my heat loss for my house was 57,540 BTUs. I replaced 130 net output boiler, and the amount of baseboard installed in my house is equal to 101,540 BTUs at high temperature. So knowing what I actually need, I can take the baseboard that's already in my house and feed it at 150 degrees. Wait a minute, that's not 180, but that's right. I've got more board than I need. So since I have more board than I need, I have more surface area. I don't have to heat it at 180. If I heat it at 150, all right, on the coldest day of the year at 150, I'm still getting a 130 back. I'm starting that condensing mode. Okay, so on the coldest days of the years in my home with a condensing boiler, all right, I'll be in that high 80s, but when we're in those, 32, 40, 45, 50, 55 degree days, I'll be in that high end condensing mode, and I'll be the most efficient that I could be. So we do our heat loss to figure out what we need, and if it's a retrofit, if I got more baseboard than I need, then I could take advantage of that by feeding it with low temperature. Underneath that particular board of compact, there's this Synergy board, which looks just kind of like it. It's a little bit taller, but the fins, the difference here, the fins are bigger and they're more fins per foot. So because of that, if you look at the output of that baseboard at 1 GPM and at 150 degrees, I'm giving you 567 BTUs per foot. That's extremely close to the 180. All right, so if I had a project from scratch where I'm designing this system and building it from scratch, it's not existing, and I went with a board like this, at that lower water temperature, I have got a much higher output because I got more surface area on the board, and I could take advantage of that. Okay, if we're going to sell high efficiency equipment, we want it to operate in that high efficiency mode. So first things first, we got to do that heat loss. We got to know what we need, and if it's a retrofit, let's see what I have and how I can take advantage of that at lower temperatures. All right, that should have answered that gentleman's question. So what I did here is I took the floor plan that you have, and we did the B2, we already did the heat loss. So if I divided the BTUs per room by 567 using the Synergy board, you can see for the foyer, I need 4 feet of board. For the master bath at 1920 BTUs, I need 3 feet of board. If I do the kitchen at 7,800 BTUs, we would need 14 feet of board. The kitchen is going to be a problem room. We're going to have cabinets there. We've got an outside wall. We don't have a lot of available wall space, so the kitchen is going to be a problem. But for this exercise, you can see how many feet of baseboard we're going to need. All right, we do the dining room at 4680, I need 8 feet. If I do the bath at 2880, I need 5 feet. We do the bedroom 1 at 6240, 11 feet. Bedroom 2 at 5760, we need 10 feet. The living room at 10,418 feet. And the master bed at 10,400, the same 18 feet. All right, so knowing the heat loss per room, now I can decide on my heat emitter. If it's already a heat emitter that's already there, and I have more than I need, then I can decide on the water temperature I'm going to use in order to deliver the BTUs I need. That's why we use these baseboard charts. Okay? Yes, sir.
This is on the Sterling website, right? SterlingBaseboard.com?
Yep. But any manufacturer of baseboard will have these charts. All right? This is nothing new. It's been around forever. Another option that you have, You have panel radiators. Now, they've been around for quite a long time. Runtal was the first guy in our market. This is Beacon Morris. We happen to represent Beacon Morris. And you can get panel radiators in different sizes. All right. What's a panel radiator? It's basically baseboard in a tighter package, or it can replace standing radiators that you've seen for years. They come decorative or they come industrial looking. It doesn't really matter. You can get very stylish looking type of panel radiators. But a product like this is something to consider when I have a room where I don't have a lot of wall space. You know, I have this kitchen with, I'm going to have my cabinets, I'm going to have my outside wall, and I'm going to have an open area where people are going to be walking in and out. I may not have enough wall space, but I got to get those BTUs in there. This may be another option for you. Or if a room's going to have a lot of, furniture in it, and you're going to have only a small amount of wall space, this is another option for you. You can mix and match this with baseboard all the time, or do the whole system as standing rads. This is what they do in Europe when they do hydronic systems. You don't see really baseboard, you see these panel radiators. Now, what you can take advantage of is you can see that based on water temperature here, it's telling you the BTUs that you'll get. All right. So if I want to even run a lower water temperature, I can, and I got the wall space, the bigger my panel rad is, the more surface area I have, then I can deliver the BTUs I need at even a lower water temperature. So larger surface area, lower water temperature will give us the BTUs that we need. Okay? So if we're looking at that floor plan, now we have to figure out how we're going to zone this. So that question came up. So this is always a very interesting question or discussion I have with contractors, especially when I'm doing a radiant design with them. And they may tell me, don't zone every single room, or don't zone as many zones as you normally do. Cut down the zones. I need to be able to get this job. I got to be sharp in my pricing. And to me, that's a dramatic mistake. Because one of the advantages of hydronic heat that John talked about last week was the comfort factor. We shouldn't have wild temperature swings. We shouldn't have blowing air that gives us heat and gives us comfort. And then when it disappears, all of a sudden we don't feel as comfortable. And the ability of zoning means I can have different temperatures in different parts of the home, which is, to me, a huge advantage, right, Rob?
I love zoning.
Rob loves zoning. In the wintertime at Rob's house, you can find snow. He likes it cold, all right? But in my house, we like it at 68. Certain rooms, we will drop it to 65, all right? My wife or I are doing a workout in one of the rooms. I don't want it 68 degrees. That's too warm, okay? So I want the ability to change temperature. So zoning equals comfort. So looking at this floor plan, when we do this live in person, I say, guys, how many zones? Here are your choices, 1, 2, 3, or 4. So when you look at the floor plan, which is now right in front of you, I've had guys say, let's make it 2 zones. They're just going to cut the house in half. The front of the house and the back of the house is 2 zones. So think about that. If it was 2 zones, where are you going to place these thermostats? Who's going to have control? 2 zones, I don't think good. So a lot of guys will say, well, I'll go to 3 zones. 3 zones is not bad, but again, think about who's going to be controlling what. So is that master bedroom going to be controlling a third of the house? Hey, they paid a mortgage, they should have control, but that may not deliver the comfort in the other rooms. I particularly like to have bedrooms zoned because everybody likes to sleep at different temperatures, okay? And, the more you read about the best type of sleep, they always recommend a cooler, dark room. So, if I can zone all my bedrooms separately, I can have more comfort, all right? So I'm making the executive decision today of going with 4 zones. Okay, Rob, you good with that?
That's what I would go with.
Rob is going with 4 zones. So I've color-coded it here so everybody can understand what's going on. So to make it as economical as possible, the red zone is taking the 2 bedrooms. So again, I just told you I like to zone them both the same, but it's not a big floor plan. If we put both bedrooms on the same zone, shouldn't be such a big deal. And now you have thermostats today that can have a remote sensor. So I could have the thermostat and say bedroom 1 if that's the north facing part of the house, and put a remote sensor in 2, and I can average the temperatures between the 2 rooms and deliver a lot of comfort. Then I have, what do I have next? My blue zone, which is going to be the dining room, the bathroom, and that living room. All right, the dining room, maybe you're going to use it every day. Maybe it's only a weekend room when family's over, but you're going to spend a lot of time in that living room. And again, you've got the ability now with these stats with remote sensors to average in certain areas. The green zone, I made the foyer, which is just really a walkthrough, the master bath and the master bed. All right, master baths and master beds should always be a zone or a separate zone each, depending on the size of that master bath. Always remember, they're the ones paying the mortgage. They're the ones that are going to pay you. You want to make sure they are comfortable. And last but not least, I made the kitchen a separate zone because it's going to be a challenge to heat it. It's going to be a challenge. So you can see I placed baseboard in all the different rooms, and we placed them on the outside walls under the glass because that would be the greatest area of heat loss. Because when we stand in front of that glass, we could feel the BTUs leaving our body because we feel chilly. So if I blanket that area with warm air, we don't feel that coldness, that chilliness. But the kitchen's a problem, all right? The kitchen's a problem. I got cabinets on that outside wall, and there's going to be a window there at some point. And I have to be able to walk in and out of the kitchen, so the back of that kitchen is probably going to be an open area. All right, so I don't have a lot of wall space. So maybe a panel rad would work well there, okay? Maybe a panel rad and some radiant underneath to do a floor warming. Or maybe we do the kitchen as all radiant. All of those are options, and we'll discuss that as we go forward. So you can see I got my combi boiler there, and we're showing it kind of in the middle of the house. This could be where the boiler was and going into a chimney. So first things first, if I'm really excited with Mr. and Mrs. Smith because they're into energy efficiency, they like what you're talking about with this condensing boiler, and they say, great, you're going to replace this cast iron boiler with condensing, and say it is going to be in the middle of the house, I do have to be able to support it. It may have to sit on a stand. Stands are available, and TI makes stands so you can support the boiler in the middle of the house. All right, or maybe you have to, actually build a wall to support the boiler. Your choice. But what's going to be tricky, first things first, is can I vent? Can I vent this boiler in this project? All right, so since we're going ahead this way, yes, we can, but you have to see if you can run the venting properly. You're going to have to grab outdoor air, and you're going to have to get the exhaust out. You can use the chimney as a chase for your exhaust, but you're going to have to line it. But where am I going to grab my outdoor air from? You got to make sure you can do that and with the proper product. And we'll talk about that in a couple of slides. All right. So any questions on how we just laid out the job, right? We've done our heat loss. We've picked our boiler. We've laid out the job based on our zoning. All right. Now we got to start figuring out what's next. Are we using pumps or are we going to use zone valves? Any questions yet, Bobby?
Nope, it's good so far.
Nope, okay. All right, so is this a zone valve job or is this a pump job? All right, so when we cross the mighty Hudson River and we go over into New York, and especially out on the island, they like to zone with pumps. That's a majority of their hydronic jobs. Over here, I think we're 70-30 zone valves to pumps, okay? I particularly like zone valves, and I have a 4-zone system in my home. So if we're going to do it with zone pumps or a zone valve system with a pump, I need to figure out the heat loss of the system, and I need to figure out the flow rate for the whole system or for each individual loop, okay? So here, if you look at this job, all right, if I was going to do it as a zone pump job, meaning every single zone going to get its own circulator, I need to measure each loop, need to figure out the length of each loop and the total BTUs per loop. So if I look at the red loop, all right, and add up the BTUs, it's 12,000 BTUs. If you remember John's universal hydronics formula from last week, GPM equals BTUH divided by delta T times 500. All right, we're going to go with a 20-degree delta on this job. That gives me 1.2 GPM. Okay? I have to guesstimate as best I can the length of that run. So if this was a retrofit, I got to walk it off, measure it as best I can. But if I'm designing it from scratch and I got the plans in front of me, I can scale it out. So my best guesstimation for the red zone is about 84 feet. Okay? 84 feet, if you look in your Takeo catalog and use our head loss formula, 84 feet times 1.5 times 0.04 would equate to 5 feet of head. So I know my GPM for the red zone and I know my head loss. Good to go. We're going to do that zone by zone. Blue zone, which was 17,960 BTUs, all right, that becomes a 1.8 GPM, okay, because it would be 1.79, all right, so we rounded up to 1.8. That's about 98 feet in length, and if we use our head loss formula, we'll get 5.86 feet of head. We could call that 6 feet ahead. Same thing for the green zone. We total up the BTUs. It's 14,560 BTUs, all right. That becomes a 1.45. We can call that 1.5 GPM. And at that length of run is about 103 feet. So at 6.18 feet ahead, it's just over 6 feet ahead. We could call it 6 feet of head. And then the black zone, which is the kitchen zone, which was 7,800 BTUs, it'd be 0.78 GPM. And that's about a 29-foot length. So it's 1.7, we can call it 2 feet of head. So quick review, by using a 20-degree delta, we took the BTUs that we have for each zone, and we divided it by 10,000. All right, because it's 20 times 500 equals 10,000. So we take the BTUs, divide it by 10,000, and we get our GPM. The length of run, we guesstimated, and then we used our head loss formula of length of run times 1.5 times 0.04 to get our head loss. Now that I know my GPM and head, I can start to pick a circulator. Any questions on that there, Rob?
Not yet.
Not yet? You okay?
I'm good.
You good? You sure?
Yeah, I mean, as good as I'm gonna be.
We got donuts.
No.
Okay. All right. So going forward here, what am I going to do? Let's get to our next page, right? So there it is again. So maybe you want to take a screenshot of this so you have the information right in front of you so you can play along at home. All right. So again, there's the BTUs, the GPM, and the head loss per zone. So now in my Takeo catalog, I can start to pick my circulator. So I'm going to show you two circulators here. I'm going to show you the 0015E3. This is a 3-speed ECM circulator.
And before you get into the circs.
Yes, backing up. Boom.
Yeah, we just want to, because we had two questions on it, the formula cheat sheet and what is the formula for head loss again. Just let them know what page they can find that on in the Takeo catalog.
Page 48. Page 48 in the Takeo catalog is your tech binder, if you want to call it, right? And this is the stuff that we use every day here at Wales Darby. So on page 48 in your Takeo catalog, that is where you're going to see the universal hydronics formula right on top of the page. A couple of stops down, you'll see the head loss formula. Okay. What else, Rob?
That was it.
That was it?
Yep.
Okay.
Thank you.
No problem. So now we got to pick a circulator if we're going to zone with pumps. And we got to do that on a zone by zone basis. So I give you two choices. I give you the 0015E3, which is a very efficient variable speed circulator that you can pick 3 different pump curves on. Or we have our VT2218, which is a delta T circulator, and that will change its speed based on actual temperature differential. So the 0015E3 pressure pump, VT2218 a temperature pump. So if we go to the 0015E3, there's your pump curves right there. So if the red zone only needs 1.2 GPM at 5 feet ahead, I can go to the low setting. All right, 1.2 is down here, 5 feet ahead brings me right up here. I'm going to basically nail that GPM for that zone. All right, just setting it on low, this will fit really well for that first zone. Your blue zone, which is 1.8 GPM at 6 feet ahead, well, 1.8 is going to get me about right here. 6 feet ahead is now up here. It would be actually the medium setting. But you know, we're close. You could live dangerously and put this down on the low setting and let it follow 5 feet ahead. So what could be the worst thing that happens on that coldest day of the year? Instead of maintaining a 20-degree delta, I may be at a 22 or 23-degree delta. Mr. and Mrs. Smith may not even notice it, all right? So, but if there is an issue, you can always then pop it up to the medium speed. But we're close here. You could live a little dangerously and run it at the low speed. The green zone, where I need 1.5 GPM and at 6 feet ahead, well, 1.5 is going to nail me right here. 6 feet ahead brings me up here. I would have to set it to medium speed. But what's going to happen, gentlemen, is I will follow that 10-foot ahead line, so I will overpump on that zone. All right? I'll overpump it probably by a GPM, but I'm going to move the water much quicker because I'm holding, the circulator is going to hold at that medium speed 10 feet ahead. So now I have the ability of squeezing down the delta T on those milder days. All right? We're close, we're better than if it was a single speed, but we're not really perfect. And the black zone at 7,800, 0.78 GPM, and at 2 feet ahead, we're down here. And 2 feet ahead brings me here. Your only choice would be to go to low. And again, we're going to over pump. So if I was to use a circulator per zone, this would be as tight as I could get. With a single circulator, it gives me options of setting speeds. Now, if you're not familiar with the 0015, is on low speed, it'll hold 5 feet ahead and run up and down here, changing its output if I was doing multiple zones off of that circulator. If I went to medium speed, you could see it's going to follow the 007E curve. And again, it'll be variable speed, but holding 10 feet ahead. And if at any time we get to this part of the curve, then we're running at full speed and we're not going to modulate. And if you needed really high head, if I'm up in this area of the curve, in this territory here, we don't modulate, we just follow the curve, as you could see here, and we're going to be running at high speed. So if I was going to zone with circulators, unless you're going to have a completely different circulator per zone, this would be the most economical choice you could do, using a circulator. And again, it's going to give you variable speed on the first 2 speeds, and you can get pretty close to the actual pump curve that you'll need per zone. Or you can use the VT2218, which will measure the temperature, all right, and actually reduce its speed to match exactly what you need. But that could get into a price issue because that is not an inexpensive circulator. So in my world, since this is not a big job, it's only 52,000 and change, right? Which means it's going to be 5 GPM. I'm probably going to go with a single circulator. Now, if I go with a single circulator, right? So let's back up again to get our BTUs to make sure we're all on the same page. All right, we need 52,320 total BTUs for this job. So that's going to be 5.2 GPM. I'm dividing that by 10,000. Now, since I'm going to use a single circulator, we're going to go with which one of these loops has got the highest head loss. And my highest head loss here is going to be 6 feet. So 5.2 GPM at 6 feet of head, I can pick a single circulator. So now if I go with my VT2218 and I pick my 5 GPM, 5.2, and I plot it at 6 feet ahead, that circulator will run. It will produce a pump curve. Whoops, here we are. And that's the way it will run. Sorry if I can get this to work. Right across there. It'll make its own curve, okay, if all zones are calling. Now, if all zones call, that's where we need to be. But if the temperature now coming back to the boiler starts to rise up because the heat loss of the building changed, because it's got warmer outside, the circulator is going to sense that temperature differential and start to slow down, because what it wants to do is maintain whatever delta you plug into it. So if we're going to maintain that 20-degree delta, if the temperature keeps coming back warmer and warmer, this circulator will slow down to maintain that 20-degree delta. If I only have 3 zones calling, I'll probably be working where you see there, probably at about 3 GPM, and again, 6 feet ahead. If I had 2 zones calling, I'll actually work there at about 1.5 GPM, 5 feet ahead. And if just the kitchen zone called, okay, well, I only need to be, a little over 0.5 GPM, or just a little under 0.5 GPM there. And, it's nothing in the head loss, but I can only go as low as that curve on the circulator. So this circulator will match the actual system curve that you need for the job based on temperature differential. I have this on my home. I've got 4 zones in my home. And as the zones open and close throughout the winter, based on outdoor temperature, that circulator is changing its output every time there's a call for heat. All right? So the comfort level in my house changed because my boiler, all right, which has some outdoor reset on it, and it's cast iron, by the way, all right, if it's been heated up already because it did a prior heat call, and then I get another call for heat, I got BTUs sitting in the boiler, I keep the boiler off, I just run the circulator. So I'm saving energy by keeping the boiler off as long as possible. But then when it fires, I also save because I'm running it as long as possible to get the best out of the burn. And my circulator is going to change its output to match the comfort level that I need. Okay? Now, I always make a joke. I'm married, so this is my thermostat at home, and she's very happy. All right? By making those 2 different things, actually 3, sizing the boiler right, being able to run at lower temperature, and having a weather-sensitive system and a circulator that's going to change its output based on temperature, has really made the comfort level in my house very, very easy to attain. And I got a happy wife, so it's a good deal. You got a question there, Robert?
Yeah, I have 2 that I want to bring up real quick. So, could a modulating boiler confuse this circulator? So,
Not at all, because all the circulator is concerned about is maintaining the delta. It doesn't care what water temperature you give it. It just wants to maintain whatever temperature differential you want between supply and return. So actually, in this system, all right, using a VT as the system circulator, because this boiler will be piped in a primary secondary, which we will be discussing in the next 2 weeks of this class. This will be the system circulator. This will be the circulator that's going to feed the system. It's not going to be the boiler circulator. So if this boiler is modulating all over creation, which is what we want, all the VT wants to be concerned about is maintaining the delta in the system. It doesn't care about the temperature you give it. If you want a 20 and you give it 100, it's going to make sure that 80 comes back.
all right, and then the next one was, how many BTUs can one pump cover up to, or should we just do it by footage?
No. Interesting. Well, TACO for years has made a whole slew of circulators. We start now at a 003 and we go up to 0018. And we make all these different circulators for different GPMs or BTUs and different head loss requirements. So no, it's based on the GPM and head for job. And you'll see in the next week's class, or the week 4 class especially, where we kind of draw the line as to say, hey, this should be a zone valve job, or this should be a zone pump job. We don't want to do a job with a lot of zones and have a large circulator there, because what can happen if I only have the smallest zone calling, my circulator is going to be way too big. All right, even if it's a variable speed circulator, it could still be way too big for those smaller zones. And now any advantages I have with modulation and things of that nature, I'll lose because the circulator is just too big. So when we cross a certain threshold, and we consider that about 130,000 BTU job, that should be a zone pump system. because I can either have a pump per zone or I can have a pump for multiple zones. And I can have multiple pumps if I got a really large system. If I'm 130,000 and less, a single circulator makes sense because then I can have a much tighter circulator based on the amount of zones that I have. So I hope that answered that question. What else you got there, Robbie?
We have an NTI guy on here, Mr. Whelan.
Oh, gosh.
He said only up to a 0018. What happened to the 26 and 54? I think he means
34. Yeah. Well, they came out and they made a great appearance and then they disappeared for a while, but I hear they're back. So yes, we have those also. So I was discussing more of the 00 series there, Steve. But on the ECM side, yes, we have our 007E, our 0015E3. All right, we have our 0018, and then we have the 0026E and 34E. So what we're referring to there, guys, is TACO has enough ECMs where we can replace with 4 or 5 circulators all the other 00s that we currently have in our portfolio. So what you're going to see going forward in your future in the world of hydronics is actually less circulators from us, but we can cover a wide range with less circulators. So that will be an advantage for you. Anything else there?
No.
Okay, good. So going forward, so instead of laying this job out with baseboard, again, we discussed panel rads, I could do a panel rad job where instead of baseboard itself, I can have the panel rads out there. One of the things I'm showing you here on the screen is another way of thinking outside the box. You have to set up a supply header and return header for your system. You can see here this is piped in a primary, secondary. So take out that boiler, put that NTI TRX in there, and that will be my primary loop, all right, because the expansion tank is on that loop. But not to confuse people, I like to call it the boiler loop. Okay, fine. And then I have my closely spaced T's, and then I'm going off into my system. I have to have a supply header and return header. Well, would you consider using a radiant manifold? If I use a radiant manifold, there's a supply header and return header built in. You have the ability to shut off each zone right on there. You also have the abilities with the actuators, which are just little mini zone valves, to zone right across the manifold. I can purge there, zone there, very, very tight package. You're basically going to be using an 1.25 inch pipe as the supply and return. That's when the majority of these manifolds are. And that's the potential of up to 14 GPM or 140,000 BTUs delivered. So if you're working in a tight area, I don't have a lot of room. I've seen these boilers installed basically in closets, and you know, the mechanic's a magician getting all this piping and pumping in there. Well, if I give them a radiant manifold that's really not much wider than about 18 inches, supply and return, I could save a lot of space. And then I'm doing a home run basically, either to baseboard or, as you see here, using panel rads. It's just another way of thinking about it, another option. All right, keep it in the back of your mind. Okay? So as I go forward here, radiant. All right, so we had a question last week about, are we going to cover any radiant? And we said yes, we would. And I'm bringing up the kitchen because the kitchen's going to be a problem. I don't have a lot of wall space. I could put a panel rad there, that's not a problem, but that may not deliver enough comfort, only because the outside wall is going to have cabinets. I'm going to have a window above that sink. That could be a cold spot to stand on, especially if it's going to be a tile floor. So maybe I'm going to do a whole job as low temperature, and I'm going to include the kitchen as a radiant zone. So now I got to figure out, well, how much tubing do I put in? What are my options? What water temperature? What's my GPM? Do I need a lower temperature than the rest of the system? How am I going to achieve that? So let's talk about this. So if I take the square footage of the kitchen, all right, 17 times 13 equals 221 square feet, and I divide the square footage into the heat loss, I get 36 BTUs per square foot. And if you're looking at that chart came from the Uponor CDAM, which is the complete design manual for radiant systems. And we look at the surface temperature. On the bottom is the BTUs. So I'm in between at 35 to 40 BTUs here, 36. So I'm kind of in between. And you're going to see some grayed out numbers and some darkly grayed out numbers. And when we get into the lightly gray numbers, we're starting to get into an area where we're going to heat the floor too high. So what are you talking about? Rob, what am I talking about? I'm heating the floor too high.
What's that?
What am I talking about? What should I care about making the floor surface temperature too hot?
Yeah, absolutely.
I should, right.
Yeah.
I want to heat the room. I want to deliver the comfort, but I don't want to cook the floor. I don't want to make it so warm that if I stand on it, my feet start to sweat. That's not comfort. Okay? And you're going to notice that, wow, geez, at that 35, and if I go up to here to an 82.5, well, that's above wood, but that's okay for tile. And if I go to the left, that's a room temperature set point of 65 degrees. Now that can flip some people out. 65 degrees is too cold in my house. I can't live at 65 degrees. Rob can live at 63, right?
Probably lower.
Probably lower, right? I like 68, but if it was a radiant room, and the building that we're in right now, all right, in the great metropolis here of Warren, New Jersey, this is a radiant heated building that we keep the temperature at about 65 because the whole floor is my radiator and I'm delivering heat to mid-chest level. All right, so if it's really warm up to mid-chest level, you're not going to be as comfortable. So yeah, we're aiming for like a 65 degree room temperature here. So now that I know that, what's next? Now I got to figure out how much tubing I'm going to need. You know, what's my method of attachment? What am I doing? And you have a lot of different options in the world of radiant. I could be above the subfloor. I could be below the subfloor. I can put radiant in the wall. I can put radiant in the ceiling. All right, it's going to work either way because radiant heat acts like the sun. It's radiating energy up from that surface. So we're not moving air. All right, and technically we're really not even heating air, we're radiating energy from that surface. So if this was a retrofit job, I'm probably not going to do a mud job as we call it, where we're going to be on top and we'll put the tubing in mud, because now I'm going to raise the floor. The area of the floor will raise by 1.25 inches before I put my finished floor back down. So another option is to do what's called a quick track, which is a 5/16 plywood that's got metal sheeting underneath it. That'll raise the floor 1/2 inch before I put my finished floor down. So that might mean you may have a slightly raised threshold before you walk into the kitchen. If the customer's not comfortable with that, I got to get below the subfloor. So we're going to pick below the subfloor here. We're going to pick joist track plates. So you can see what I'm taking here is the square footage of the kitchen, and I'm multiplying it by 1.5. Because 1.5 tells you that we're going to have an active loop length based on 8 inches on center. So I'm underneath the floor in between the joist bays, and I should be 8 inches on center from tube to tube. All right, so we're pulling the tubing down the joist bay. There'll be basically, you know, one loop per bay, and I should be 8 inches on center from tube to tube to tube to tube. So we take the square footage times the 1.5, and that tells me I need 331.5 feet of tubing. Now, could I do that as one loop with 1/2 inch pipe? Yeah, but you don't want to. All right, you really want to do it as two. So that's why I multiply it by 0.5, and I'm going to need a 65.75 foot loop, and I'm going to need 2 of them. But now I have to also add in footage based on getting the tubing into that floor, okay? So my manifold is not necessarily going to be right underneath that floor. It could be in the mechanical room a few feet away, okay? So in this instance, we're going to say, yeah, I got an extra 10 feet per loop. So that means 10 feet on the supply, 10 feet on the return. So there's additional 20 feet per loop. So now I need 2 loops for this kitchen at 185 feet each. Then I got to figure out how many tracks I'm going to need. Now these joist tracks are aluminum tracks that screw up to the subfloor, and then there's a channel underneath it that I snap the tubing into. So in this instance, you'd make sure that your joist bays are clear, no protruding nails or anything like that. And if there are protruding nails, you have to cut them off, and you don't just nip them off. You're going to have to cut them off and grind into them, kind of into the subfloor a little bit, to make sure there's no metal in contact with those plates. Because remember, we're going to heat the plates. The plates are going to expand and contract. We don't want to hear any squeaks or things of that nature. So if you do have protruding nails, you got some dirty work you got to do. So we make sure that's clear. I put my joist tracks up there. How many do I need? Well, we give you another formula there. As you can see, that to figure out my joist track plates, I multiplied my total tubing by 0.2125. I need 70 plates. So now I know my water temperature. Actually, no, now I know the BTUs I got to deliver. Now I know the plates, and now I know how much tubing I'm going to need. So now what's next? Now I got to figure out my water temperature. So this chart, again, comes from the CDAM, and the CDAM is showing you for joist heating, 8 inches on center, and if I'm going to maintain a room temperature of 65 degrees, I find on the chart on the left-hand side the BTU where I'm playing. All right, so I need 36. The 35 line there is easy to see. I'd be slightly above it. I'm going to go with the 35 BTU per line curve. And I picked that curve because the R says 0.5. That's the R value for the finished floor. And if it's tile, that's basically what we're using. All right, you do have the ability to look up every single R value for any type of finished floor, but on average for tile, it's going to be a 0.5. If it was wood, and nobody was telling us exactly what it was, we're going to use a 1, but we're using a 0.5. So I plot it on the chart, and if I go straight down, you follow along, Rob? If I go straight down,
Yep.
All right, at a 10-degree delta, I'll be at 133-degree water temperature, and if it's a 20-degree delta, I'll be at 135-degree water temperature. 99% of the radiant jobs you do are going to be at a 10-degree delta. We're going to go with 135. So I know my BTUs per foot. I know the amount of tubing I need. I now know the joist track plates I need. And now I know the water temperature I'm going to run. So next, we got to figure out GPM and head, because this is going to have its own separate circulator. All right?
I have a quick question.
Quick question. Shoot, baby.
Are we going to be discussing primary, secondary today?
Not today, next week.
Because I have 2 questions here that I believe directly correlate to that, if you want to just touch upon them real quick.
Let's touch them.
All right. So the first one is pressure balance bypass valve in single pump multi-zone valve is an option.
Yeah, but as we like to call it, it's a Band-Aid.
Right. Primary, secondary piping would alleviate the issue he's concerned about.
If you're not sure what we're talking about here with primary, secondary, what that does is hydraulically separates 2 different flow rates. So I'll have a flow rate for the boiler. Let's say the boiler needs 10 GPM, but my system, maybe it needs 15 GPM. With 2 closely spaced T's, I hydraulically separate those 2 flow rates, the 2 circulators in the system circulator and the boiler circulator never see each other. So the boiler is supplied with the GPM it needs, the system is supplied with the GPM it needs, 2 circs don't see each other, okay? If I have multiple zones on the system side and I'm going to use a pressure differential bypass valve, basically what I'm saying is I'm going to take a single zone circulator, that just does 1 speed all the time, and by adding this pressure differential valve, I'm going to help make sure I don't overpump in different zones. But that requires some extra piping to come back. All right? It's a Band-Aid. I've got circulators that can do it for you without that extra piping or that valve by temperature and or pressure. All right? So not needed, but you could use it if you choose. Sure.
All right, and the second question you pretty much just answered. I would remove the pressure differential valve and put in a constant pressure pump on the manifold.
Well,
basically along the same line.
Yeah, it depends. So I can see a couple of guys really zoned in on this picture where that pressure differential bypass valve is there. I understand that. I haven't done a radiant system yet where we had a pressure differential bypass valve. All right, because I've got these circulators that can change their speed based on temperature and or pressure. All right, back in the day, when injection mixing was the hot thing to do, because that's where you were able to do your outdoor sensing and change speeds based on outdoor temperature. Yeah, you probably would have used a pressure differential bypass valve, all right, because you probably had a circulator that was a little bit too big and you needed to really dial it in. And that's where we'd use a pressure differential bypass valve. The system that actually runs our GPM and head here was a pre-made package that you bought from Uponor at the time. And in there was primary, secondary, injection mixing, and we had a little pressure differential bypass valve per zone. So you can dial it in and get it as tight as you can be toward the requirements of the job. We don't have to do that today because we have these smart circulators, when we say smart, they are smart, but we still have to size them. And we do have also mixing devices that also sense outdoor temperature, and they change their output. So I got a boiler that can change its output. I got a mix valve that can change its output based on temperature. And then I got circulators based on either pressure or temperature that'll change its output. We can dial this all stuff, our system in to be as efficient and as tight as possible. And so we wouldn't need those other valves. All right.
Yep, absolutely.
How am I doing, Rob?
That was perfect.
That was perfect.
In order for for them to understand, next week I think would be something that they shouldn't miss.
Oh yeah, next week is going to be good. Next week is going to be good. Well, they're all good. All right, they're all good.
So.
What are you laughing at, Brett?
One other quick thing. Was there a handout from last week? What was this guy looking for? It's like a TACO training sheet or something like that.
Well, basically, when you signed up for this training class, you're right. The first time you signed up, we showed you that you should have had these downloads, right? Is that correct, Chris? On the initial sign up for the class, right?
If they attended, it would have been in the chat box.
Right. So and when you first attended, especially last week, any and all downloads would have been there. All right. So when you see those downloads, you want to download them because this is what we're going to use. All right. So you can play along. All right. Send us an email. All right. To either myself, jadapalma@walesdarby.com, or rclemens@walesdarby.com. If you can't find us or you're not sure where it is, and we'll send you an email with those downloads. Okay. Anything else there, Robbie?
Nope, we're good for now.
All right. So now that I know everything I need up to this point, I got to pick my radiant GPM and figure out my head loss. So you can see there's another chart there from Uponor showing you at 100% water. Okay, I'm not putting glycol in this system at all. And based on the BTUs per foot, so there is a 36 on the left-hand side. And you can see 8 inches on center. I would take that loop that I have, and I'm going to multiply it. Whoops, I'm going to multiply it at 0.00486, right there. So if I take that loop, okay, 185-foot loop times that 0.00486, I get 0.899. We can call that 0.9 GPM per loop. So it's a 1.8 GPM total. And then I got to figure out my head loss. So I'm showing you a chart there that's right out of the TACO catalog for PEX pipe. That's right on page 48. All right. And on a 0.8, what are we using here? Yeah, we're using a 0.8. So on a 0.8, so per loop, it would be 0.02 per foot. And that comes to 3.7. And since there's 2 loops, it's going to be 7.4 feet ahead. So now that I know my GPM and I know my head loss per loop, I size my circulator. So it's really not a lot of GPM, all right, 0.9. All right, we're a little over a half a GPM for that kitchen. 7.4 feet ahead, we could use a 0015 E3 set at medium speed, all right? So let's make sure we all see that. We can back up, all right? We can back up to the 0015 E3 at medium speed. Geez, I'm sorry, pointing at the wrong thing. 0.9 down here, a little over 7.5 feet. We would set it at medium. We'd operate here, so we would squeeze our delta a bit, all right? Or if I use the VT2218, at 0.9, again, I'm pointing to the wrong place, down here at 7.4, it'll run exactly right there. It'll create that curve and right there. So if I want to nail it, I can go to VT2218. If I want to get close, 0015E3, set at medium. All right? All right, so we figured out our radiant. One last thing, I may have to mix down the temperature. So on this particular project, if 150 degrees is going to be my supply water temperature, all right, because I got to base it on the coldest day of the year, all right, and I only need 133, I got to mix down. You've got options. There are standard mix valves you could use. Taco makes the I valve, which is a 3-way, 2-way, or even a 4-way mix valve that has outdoor reset built into it. You give it 24 volts, you run a sensor outside and a sensor on the piping, and it'll determine its port opening based on that temperature that is needed, based on outdoor temperature and supply. Or you can use a fixed temperature mix valve. So on the chart here, I'm showing you the Taco 5000 fixed temperature mix valve. And you can see on the chart based on GPM on the left, all right, depending on the size of the mix valve, it'll tell you what the actual pressure drop will be through there. And that's important because you do have to add it to the total head loss. So if you went with a 3/4, you'll also see another set of numbers in parentheses where it says CV equals 3.5. So they're telling you at that valve, if you gave it 3.5 GPM, which at a 20-degree delta is 35,000 BTUs, you'll impart 1 PSI of pressure drop there, or 2.31 feet ahead. I only got to move 0.9, all right? So I'm a little over a half a GPM. So I'm basically going to be adding another 0.19. If I bump it up to that 1 GPM, head to my circulator size. So it's not a lot of extra head, but you do have to take that into account. That can be a big deal if it's a bigger radiant system and I'm using a single circulator. I can actually move you into a different size circulator. So you do have to be aware of that. All right? That makes sense?
Yes, sir.
Cool. Robbie is typing away. All right, so going forward, we've done all this work. We did our heat loss. We figured out BTUs per room. We figured out different ways of delivering the heat per room. We figured out how to zone it. We figured out how to take care of a problem room, all right, if I couldn't get enough baseboard or panel rads in there, okay? You know, and now we've been talking about, retrofitting cast iron to condensing. Things to think about here, and this is why this screen here is really important. Based on your area that you're working in, and this 5,600 degree days is pretty close to the area that we're working in right now. This chart's showing you how often we actually run at a full capacity. And it's showing you 8 days or maybe 3%, okay? The most days, 65 days out of this heating season, we'll be running at 40% capacity. That's pretty wild. Remember, we figured out the heat loss based on the average coldest. And 40% of the time, or 65 days, we'll be running at, 30% of the time, we'll be running at 40% capacity based on 65 days, all right? At 49 days, we'll be running at 60% capacity. So you can see it's pretty rare that we get the full output. So that's why we want to be able to design our system as tight as we can be. All right, because the majority of the time we're not going to be at full capacity. And if you think about it, if you've nailed it and you're at full capacity because we're really, really cold, that boiler should never turn off because I've actually nailed the BTUs that's leaving the building and I'm replacing them with the exact amount, And then when we're in those milder days, especially if the boiler can modulate and change its output, I'll be more efficient, okay? We don't want to oversize. And if you remember from earlier in the presentation, when I picked the combi, I'm not oversizing the combi to meet domestic load. If the domestic load is much larger than the system side, we do a different type of domestic system. Maybe an indirect, all right? And maybe more volume in the indirect, which we'll be talking about in the next couple of classes, or maybe we have a separate heat source just for domestic. All right, so cast iron boiler systems, and we're getting near the end here. Cast iron boiler systems, very durable. They last a long time. They run at high temperature, don't need a lot of maintenance. Just check the flue to make sure the flue is really clean, make sure the burners are clean. But other than that, it's going to rock and roll. Can you make a system like this even better? Well, yeah, you can. You can add outdoor reset to a system like this. This is what I have in my home. I do have a cast iron boiler. All right, why didn't I go condensing? Venting issues, also budgetary issues, okay? So I went with a tightly sized cast iron boiler. I added the Taco outdoor reset to the system, and I'm saving 20%, okay? I got the potential of saving of up to 30, but I'm saving 20%, which is good enough for me based on my needs. You'll see there's 3 circulators here, and there's 3 mix valves on this system. Most radiant jobs, if it's a whole house, will probably be a 2 temperature system. But if it is a 3 temperature system, fine. But if I change those mix valves out to a weather sensitive and outdoor reset mix valve, I add more comfort to the system. Now, if you're sitting there thinking like, geez, he wants to sell me all this stuff, yeah, that's my job, right? But if you think about it, if I'm offering these options to the homeowner based on comfort level, yeah, you are upselling, you'll make more profit, you'll deliver more comfort, and that ultimately is your job. Right, Rob?
Yes, sir.
If I put stuff in your house and I make it work and you're not comfortable, did I do my job?
No, sir.
And Rob will find me.
Will you get a phone call? Yes, you will.
So you don't want phone calls, you want happy customers, you want referrals. We're delivering comfort here, so that's what we're preaching. That's the whole reason why we've even done this class this week. How to figure out the proper size system to deliver the comfort needed. So these boilers are going to last a long time, very durable, but you can make them better by adding an outdoor reset control. It's not a big deal. When they use our Taco SR or ZVC panels, you can plug in our PC700. We will talk about that in upcoming weeks, I think week 4 especially, all right? Now your combi boiler or condensing unit, all right, so these are the older NTI boilers here. We have to change that screen, all right? And here I'm either going to be going with zone pumps or 1 pump and zone valves, heat only, or a combi. Again, I can't stress this enough. Size the combi based on the GPM you need for the domestic. Do not fall into the trap of oversizing the combi for domestic. That'll lead to banging and short cycling and not a happy customer, and they're not going to save anything, all right? Because the whole idea on a combi is I'm not heating a tank of water, okay? But we want to size them correctly. So these guys should last, if you maintain them, about 15 years, maybe 20 years. But that requires maintenance. That requires pulling the burner out after 1 year of service to see how clean the heat exchanger is. That means checking the venting to make sure the venting is clear, okay? Very important. Making sure, all right, that I am not overfiring because of poor venting and damaging the heat exchanger. So this is built-in maintenance. This is another way to be profitable on these jobs. If you vented it correctly and you're seeing a very clean heat exchanger after 1 season, you probably don't have to pull that burner for another 2 years. So the maintenance is something that should be done. That's the way these appliances operate. You do have to let Mr. and Mrs. Smith know, and you want to make sure you take advantage of that, all right? They should be efficient, but only if we design them to operate in that condensing mode. If you're sizing this guy and it's firing at 170, 175, 180, it's a fancy looking boiler with a great looking jacket on it and a cool control, and you're not going to be in that 95%. No way, no how. At 130 return is when I start condensing, and the colder return gets, the higher the efficiency goes. Okay? We could take advantage of the turn down because this gets us tighter and tighter to the actual heat loss of the building. Okay? So when they first came out, 5-to-1s, then we got the 10-to-1s, and now we got 11-to-1s. All right? So they're getting even tighter and tighter based on our job requirements. But a very important thing to think about is the venting of these products. Based on your water temperature, yes. So if I'm going to supply 150 degrees on this particular job, right, to take advantage of the existing baseboard that was there, that means my stack temperature will be 20 degrees hotter. So if I need 150 at the time, the stack temperature will be 20 degrees hotter. That means the stack temperature is 170 degrees. And if you vented it in PVC, gentlemen, you're outside the temperature range for PVC. PVC's got a max flue gas temperature, and this is what the industry came up with, not the PVC manufacturers, of 140 degrees. So that means my supply water temperature would have to be 120. So that would mean I'd have to do the whole house as radiant or as a low temperature panel rad system or low temperature baseboard system. You could do that if you've done all this work up front. So you have to be aware of this. The venting is critical on these components. It's very important. And I'm going to do two pipe because I need exhaust, but I need air intake. Air intake all day long with PVC, but on the exhaust side, use the proper product. And if I'm using a combi boiler, all right, and I have a decent domestic load, maybe it's a big house, so space heating and domestic's pretty high, and I'm going to be using domestic all year round, I'm going to high fire that boiler, you're going to need to use the right product. So what I'm showing you here on the screen is Centrotherm, another product we represent, and this is venting material made for condensing boilers. This pipe is only made for venting. It's a poly pipe. It has a 230 degree rating. And to get that rating, I have to be able to have a 70 degree safety factor in there, Rob. So that means up to 300 degree temperature, this pipe will operate. Okay? So you want to use this type of product. You can get it in a flexible type of configuration. So if I need to vent through the chimney and the chimney's got an offset, I can use the flex to get it down there and grab outdoor air from the outside, all right? Not through the same chimney. If I need a concentric, which would be a pipe within a pipe, we have that too. So you can see on the screen where I can vent through the sidewall or through a roof penetration, bring up my two pipes or bring the two pipes to the side, but have one penetration going through the wall. I get my exhaust through the center, air intake around the outside of the exhaust, okay? So first things first, when Rob, myself, John are out there on a job and you're asking us to give you some design ideas or how would you lay out the job and you want to do condensing, first thing I'm looking at is how can I vent it? And I got to make sure I vent it properly, okay? So NTI as a manufacturer gives you a piece of CPVC pipe about 5.5 inches to come off right at the top of the exhaust if you are using PVC, because that would be the hottest spot of the venting system. So we see these boilers go in and guys don't use that, and you have to if you're using PVC and if the PVC will be within temperature range. If you're not, then you go directly to this type of product. It'll be less than the stainless, the AL29-4C type of product, which can handle any temperature, but this is very cost effective and it's within line of PVC pricing since their prices have gone up. So you want to make sure you vent these systems properly. We have a class just devoted to the venting on this. All right, my NTI, that company as a manufacturer, gives 11 pages devoted to venting for these type of boilers. Very, very important. Can I vent this properly? And if I can't, you don't want to force it in there. It's only going to cause problems with the performance of the appliance. So just as we get to the end here, big deal on the condensing boiler to make sure everybody understands what condensing actually is. What we're doing is cooling down the flue gases. Now, Anthony talked about this very deeply when he did his low temperature class. And what we're doing is, since my return comes back cooler, it cools down the flue gas temperature. So the flue gas, you cannot see, it's a gas. If I cool it down, you start to see the white plume outside. That's not a gas anymore, that's a vapor. And if I cool the vapor down even more, it turns back into a liquid, and inside that liquid is latent heat energy. And that's what we want to capture back into the boiler. So the heat exchanger inside this boiler is made to be able to capture that latent heat energy and not corrode. Okay? So we're absorbing that latent heat energy. So what does that mean? For every gallon of condensate I produce, I'm actually going to be able to reabsorb 8,080 BTUs back into the system. And that's when they're in that 90 plus condensing mode. So to think about it this way, if I'm at that 90 plus percent, say I'm at 95, that means for every dollar I spend, 95 cents is heating my house and only 5 cents is going out the chimney or the exhaust venting, versus a cast iron, which is at 82%, for every dollar I spend, 82 cents is heating the building and 18 cents goes out the flue, okay? That's why we do this, gentlemen. So we want to make sure they condense, okay? So for every 1,000 BTUs, I should produce 1 gallon of condensate per hour. And this chart's showing you at 130, this is where we start in the condensing mode. But that's not my highest efficiency here. I'm probably at that 89, all right? And then as I start to get colder, 120, 110, all right? Now I'm starting to get up into that high 90s, and if I can get below 100 on the return, that's where I can get up to that 95, 96% efficiency. So all this work to make an efficient system, but I have to do this work, otherwise I'm just flat out guessing. Okay? And if you want to be at a price advantage versus your competition, this is the work you want to do. Now, if after all of this you're saying to yourself, I don't have time for this, partner up with a wholesaler who can do this for you, and there are wholesalers out there that do that, or you partner up with a rep, hello, where we can help you do this stuff. Okay? The contractors I know that do this work, as Anthony said 2 weeks ago, which really hit home with me, they lead. They're not following what everybody else is doing, they're leading. They don't care what the competitors do, they lead. This is what I do. This is it will be the best system for you, Mr. and Mrs. Smith, because they have all this knowledge, they're able to present that. And if Mr. and Mrs. Smith say the prices are too high, well, guess what? They have other options for them. This is why we do this, gentlemen. This is what makes us professionals, and this is what we want to do going forward. So, Robbie, any other questions? You look like you're chomping at the bit.
I have one guy wants us to go back to the previous slide. I'm not sure exactly why. He didn't say, but
Which
go
slide?
back to it.
This one?
Yeah, maybe he'll come out with a question for that afterwards. In the meantime, I have another. I don't know if this was a question or if it was a statement, but the two loops, when you're talking about I'm assuming he's talking about a multiple zone system off of a single pump. Those are, when adding your total head, it's in parallel, not in series. As in?
When I do a single pump and I have a zone valve system, I'm looking for the worst head loss out of all the loops. I'm looking for the worst one. So on this particular job, our highest head was 6 feet. That's the only one I have to worry about. If I got a 5 foot on another loop and a 2 foot on another loop and a 1 foot on the other loop, we're not concerned about that. We're concerned about the highest head loss.
Right. We're not adding them together.
No.
We're going to the highest.
So keep this in mind. GPM is cumulative. So all the GPM per loops are added together. So we know the GPM we need to deliver, so we can deliver the proper BTUs. But the worst case head loss, or the highest case head loss, is what we use to figure out the other part of the equation, to figure out our circulator size. Okay? Is this the screenshot he needed?
Yes, that's what he was looking for. I did ask him if he had a question on it, so I'm just going to wait for that response.
Okay.
And then there's another question here about flow control in the ceiling. I don't know what he's alluding to there, but he says flow control in the ceiling, why?
I'm not sure. I don't understand the question either.
Yeah, that's...
Is he referring to maybe doing radiant in the ceiling, and how do I protect it?
Not sure.
You know, when you do a radiant system, regardless of where it is, floor, wall, or ceiling, there's always insulation under, behind, or on top. So we drive BTUs into the room.
You said something about a picture that you showed, flow control in the ceiling.
I'm not sure. We didn't show a picture with a ceiling install. Not sure. What else you got?
You show 3 pumps and flow control on the ceiling. Go back to the.
Well, maybe it's up on the wall, and he's considering that the ceiling. Let's go back. Is he talking about? Well,
That's back further.
Back further?
Yeah.
That's on the wall. That's on the wall. He's talking about something like this. I mean, there's nothing on the ceiling.
Is there a flow control up there? I got the.
Well, there's a pressure differential bypass at the manifold, but again, not necessarily needed at all, especially when I use a variable speed circulator. So I don't have anything on the
And
ceilings.
that says a wall installation photo, so go forward again.
Wall installation photo.
This one here?
Oh, the flow check is up in the underneath the floor on this particular job. Yeah, he's got it on the horizontal run, not the vertical, because it has to be mounted that way. It's a horizontal flow check.
Okay.
Yeah, so that's why it's there, not on the vertical side of the pipe, because there are horizontal flow checks. So even there, with that circulator and those flow checks deliver more resistance than an IFC circulator. IFC means you've got an internal flow check in the volute of the circulator. All right, so I'll get a better performance because I'll have less resistance with that flow check internal to the circulator versus the flow check that's, you know, separate in the system. And they're horizontal, so they have to be in this direction. If they were vertical this way, then I'll have the flow check always not operating properly.
Okay. But aren't checks built into the pump?
Yeah, that's the IFC. Most of the manufacturers, at least with us now, you can buy the circulator with it already installed, but you can also, especially with our ECM, it's going to be in the box. And when you take the cover off, it's going to be right there on the flap. You cannot miss it, and you have your choice of using it or not. Not every job needs an IFC. I zone with pumps, I need an IFC, I need a flow check. I do a zone valve system, single circulator, no need for an IFC. What do you got there, big guy?
That looks like it's gonna be it, I think. Yeah.
We're good?
Mr. Whelan said, thanks for a great webinar.
Thank you. I appreciate it because Steve is one of the best hydronic guys out there. I always go to his webinar. Thirsty Thursdays, which I believe is this week. So if you guys are not on the NTI webinars, you should. Great information. Ellen Rohr is going to be the guest. So if you want to learn how to run your business as a real sharp business, tune into the NTI Thirsty Thursday webinar. That's a good one. All right. Next week, week 3, we will be understanding near boiler piping, component systems. We're starting to get into that primary, secondary type of stuff. You're going to be given tasks to size circulators and pumps and all that kind of happy stuff. Make sure you have your downloads ready, okay? So if you have no further questions, thank you very much for tuning in today. We had a lot of fun. Sorry for my glitch in the beginning, but hey, it's live. It happens, okay? And we'll catch you next week. Thank you very much.
Email.